Welcome to Institute Seminar Days 2024, and the chair of the first session is Sayantan.
And so we can just get started. So our first talk is by our colleague Srihari, who will tell us about baryogenesis. And it's a blackboard talk, so we will have a very informal discussions on it. Please, Srihari.
Okay, good morning everybody. So thanks to the organizers for putting this together. My challenge would be to stick to the time. I'll try my best. So there's a lot of preliminary things I felt I should say. I'll start with that, hopefully quickly, and then get to what is the crux of baryogenesis. So, and also if my writing gets too small and it's not visible from the back, please let me know. So I'll try to consciously keep it a bit bigger. Baryogenesis. So what is baryogenesis? So baryo stands for baryon, and genesis is how did it come about, or origin. So we want to learn about the origin of baryons, and where is the setting? It is the universe. So we want to learn about the origin of baryons in the universe. So universe is everything that we see around us. So we are in fact made of baryons. And a distinction that I would like you to keep in mind is we are made of baryons but not antibaryons. So that's a crucial thing in baryogenesis. So the question is, how is it that everything that we see around us is all baryons but there are no antibaryons? So I'll say a little bit more about it, but that's a crucial question we wish to answer. So what are these baryons? So I told you we are made of baryons. So these are, let's say, the proton, neutron, and there are a bunch of other baryons. But for our purposes here, we'll just stick to these. These are the stable baryons. In fact, the neutron is also not stable. If it's a free neutron, it will decay. So really the only stable baryon is a proton. And you know, mostly we are made up of protons and neutrons in the nucleus. So everything we see around us is put together by protons and neutrons. And of course, we also have electrons, which is not a baryon. But for charge neutrality of objects around us, there are equal number of protons and electrons in the universe, we think. And there is no reason to suspect this. So if I can answer how many protons there are in the universe, automatically I will assume that there are the same number of electrons for charge neutrality of the entire universe. So I will not really keep track of electron. It is just equal to the number of protons. So neutron, the number is little bit lesser than the number of protons if I count in the universe. So this is a parenthetical remark. So I'll mostly not refer to the neutron, but they are around. So mainly we will keep track of protons. And in the universe, what else is there? We can have photons, right? Photon is a light particle, the particle of electromagnetism, light. So in the universe, we can observe photons. And we have neutrinos. But neutrinos are so weakly interacting that they're basically just sitting there not interacting anything. They're decoupled. They're so weakly interacting that they don't do much. So for this talk, I'll forget about that. So mainly the players are the protons and the photons. So I want to ask how many protons are there in the universe that we see. And of course, because the universe is a temperature bath, so it's a bath in thermal equilibrium at early times. And so it is a gas of protons and photons interacting thermally. So it's a thermal system. So the universe to us is then a box. I will consider one region of the universe. It's let's say a cube of some 1 meter by 1 meter by 1 meter. I look in this volume. And if I look at very early times, we think the universe, we are very sure that it began in what is termed as a Big Bang, a very hot temperature phase, right? And so this Big Bang, after the Big Bang, the universe just expands and cools. Whenever a gas expands, it cools. So this is at very high temperature, and we pick up the action when, let's say, the temperature is still incredibly high compared to our human temperature, something like 10 to the 16 Kelvin. So let's just say that the universe from, who knows, some incredibly high temperature eventually cooled to some temperature like 10 to the 16 Kelvin. And here I want to keep track of protons and photons in this temperature bath, right? And so in particle physics or in special relativity, quantum mechanics, one of the basic principles is that whenever you have a particle, you also have its antiparticle. So we have antiprotons also necessarily in the framework, right? And in the lab, we routinely see that if I have a photon, it can split to proton-antiproton pair. That's something which we routinely see in the lab. Similarly, if I have a proton and an antiproton, they can annihilate each other to just give me light photons. These processes are routine. We observe them, there is no doubt about this. But important point is whenever a photon splits, it will split to one proton and one antiproton, never a single proton, because that would violate charge. So it should always split to a proton-antiproton pair. So these are in thermal equilibrium in the early universe. So let me denote a proton by an open circle and an antiproton by a solid circle, right? So I don't know why they came out different size, but okay. So there are some number of protons and some number of antiprotons, and so that's and they are in equilibrium with a lot of photons, right? At some temperature T, so the number of photons is given. If I tell you what is the temperature, the number of photons is given by thermodynamics, basic thermodynamics. I can work out how many photons there are. So this is where we start at 10 to the 16 Kelvin, and then we ask, as the universe cools, it expands. So the present day universe has become bigger. This region expands. So it has cooled. And since this process can happen, proton and antiproton keeps annihilating, and at some point the reverse reaction becomes energetically unfavorable. So this shuts off while this keeps happening. So it depletes the number of protons and antiprotons. So these things will annihilate with each other to give you photons. So late time, there are many more photons, right? Because everything is annihilating to photons, incredibly large number of photons if we look in our present day universe. But there are a few protons and antiprotons. What are left over, right? So this is what you would expect. A gas of protons and antiprotons in equilibrium with photons, expands and cools. And since there are annihilations of protons and antiprotons given by this, they should always annihilate pairs, right? So they get rid of each other in pairs. And you should be left with such a state now. But this is something that we have made observations of. We can look in our neighborhood, galaxies and so on. Oh, I should have changed the tune, but anyway. So when we make observations, remarkably we find that there are no antiprotons. There is only this one left. And for charge neutrality, I told you there is somewhere one electron. If there is a proton, there is also some electron somewhere to make it charge neutral, right? So this is the universe that we observe. There are no antiprotons. And it's a big puzzle in particle physics. How, right? How did this come about? We would expect naively that there is an equal number of protons and antiprotons starting from a symmetric early universe. But we find that this is not symmetric. And if I look at the number of baryons, take the difference with number of antibaryons divided by the number of photons, this is this ratio which is termed as eta. This is an observation that has been made, and we find roughly this ratio is around 10 to the minus 9. So for every billion photons, we have about one proton in the large scale universe. So it's what we are made of on Earth, it is a very highly concentrated like place because of gravity. But if you average this over the entire universe, this is the number that we observe. Like for every billion photons, we have one proton that is left over. So the question is, how do you explain that in theory, right? I mean, this is observation. And so that is where we as particle physicists come in, and we try to ask, can we explain this kind of an observation? So you could try in any theory, if you have to explain this kind of a process. Shakarov in 1967 gave 3 conditions. In any theory, 3 conditions, he said, must be satisfied. Oh. So I think I better wind up. He gave 3 conditions. So one is baryon number must be violated in some process. Second condition, C and CP violation should be present. This just distinguishes particles and antiparticles. That must happen, otherwise you always end up with equal things, whatever you start with. The third thing he said is departure from thermal equilibrium. If the universe never deviates from thermal equilibrium, then whatever you produce, the reverse reaction will erase it. So Sakharov said these 3 conditions must be true in any theory. And our beloved theory is the standard model. We have tested it very well. So we can ask, in the standard model, are these 3 conditions there? And remarkably, yes, all of these 3 conditions are present in the standard model. And so people have gone and computed how much of baryon asymmetry will you find? Like, can we explain 10 to the minus 9? And the answer came out, no. It falls short by about 5 or 6 orders of magnitude, and that's the puzzle. And so my attempt has been to take theories beyond the standard model. For instance, I am looking at a new particle, which I would call chi, which decays to a baryon, but it is constructed to be a Majorana or fermion, so it can decay also to an antibaryon. And if I can arrange in my theory that the decay rate of chi going to baryon is not equal to the decay rate of chi going to antibaryons. Again, I will implement these 3 conditions for that to happen. And the attempt is, can I explain this 10 to the minus 9? So that's my work in the last couple of years. Okay, I'll just stop there.
Thanks, Srihari, for setting the stage, and we have time for one question, if you want to ask.
Why does one look into the Shakarov's condition?
Yeah, so it is just that if I have some process, let's say chi goes to B, baryons, in thermal equilibrium there is also B goes to chi.
Yes.
If these 2 are in equilibrium, whatever baryon number that I produce will get erased by the inverse reaction.
So what about looking for the non-equilibrium steady state rather than the equilibrium state?
Non-equilibrium phases.
Steady state, in non-equilibrium steady state you can...
So one does, technically doing this, one solves the Boltzmann equation.
Okay.
So you deviate from thermal equilibrium and then you ask what are the steady state values of the number densities. Yeah, technically that's how you would do the calculation. So that's what Sakharov is saying, you have to deviate from thermal equilibrium. Otherwise, inverse reaction will always erase.